Good morning, Ola.
Hi, Dr. Killian.
How is your day?
Good. I thought you said you were going to do this from home instead of going to.
I'm not sure. I prefer to come in person. It energizes me a little.
It will be just you.
It's a little exercise.
Okay.
Oh, hello, Hanmand.
Good morning.
Let me make you. Hello, Emir. Let me make you all co-hosts so that if anyone joins during the meeting, you can admit each other. So, hello, Umar. Hello, Hadassah. So if you see anyone joining, please admit. Do not check with me. Okay. Many thanks for supporting these meetings by visiting. Let me set up screen sharing. Did anyone admit Amara? So, yeah, hello, Amara. Hello, Haley. Okay, I think we are all set now. So do you see the slides? Okay, very good. So we are in the third chapter of this class, and the goal is to get ideas and equations behind the density functional theory, which is a workhorse for most practical computations. In a couple of weeks, we will make presentations based on the skills that we accumulate in the lab. And before going forward, let me bring your attention to the homework that I wasn't checking emails this morning, but I hope majority of the class attendees have completed it. So the assignment was to plot the gap as the function of number of unit cells, right, in the simplest conjugated oligomer. And here is the homework from Payman. Instead of showing gap, he did show energies of HOMO and LUMO, but it contains the same information. So the gap will be the energy of set of HOMO and LUMO, which changes from about 4 electron volts to about 1 electron volt. So you do see the trend that in this one-dimensional nanostructure, the gap decreases as the length, right? And there is, what I'm telling you right now is not for the course, but it's a little background, but it will be quite useful for all of us in going forward. So as we go to a longer and longer chain, the energy of LUMO approaches the energy LUMO of infinity, right? And energy of HOMO approaches the energy of HOMO of infinity. So there is a connection between background theory of particle in the box and everything we can do for nanostructures. You may have asked this question to yourself, but let me verbalize it. So energy of LUMO as function of length of this structure is equal to energy of LUMO in the limit of infinite chain plus the constant times 1 over L squared. So when L equals infinity, it goes, this quantum confinement correction goes to 0. When the chain is very short, it increases substantially. And same for the HOMO. Energy of HOMO as function of L is whatever it is at infinity. And we can just put all signs inside of the constants, and it also depends as 1 over L squared. So if we subtract LUMO from HOMO, then the gap will be subtraction of the fundamental gap in the limit of infinity plus the correction that also depends on L squared, right? So by making the nanostructure smaller, we limit the space where electrons can move. So we confine them in the limited space. Therefore, it's called effect of quantum confinement. So any of you who will do nanostructures for the project may address your results in this style of interpretation. And here is I think it is homework of Sarah. She's showing the gap as function of length, right? So in some sense, what I did show is a answer key for successful completion of this homework. Okay, let's go through the slides. So what are we going to get in this part of the course? We are going to look on the first Hornberg theorem, and those of you who did attend yesterday noticed that the density functional theory, I wouldn't say neglects, but skips focus on wave function and focuses on density. In many years, so the proto-DFT, Thomas Fermi theory, was designed instantaneously with the design of Schrödinger equation, like in 1927, but it was just a theoretical model. The actual DFT theorems were offered at the early 60s, but a majority of the community was very skeptical about it. And it was a time when computers were not yet available to do many of calculations. It was basically theoretical descriptions. A lot of people were skeptical and telling that one cannot get energy without a wave function. And the developers of this theory experienced a necessity to argue with colleagues and prove that a theory that can predict total energies of molecules may be based only on electronic density. It was considered as something unusual, like almost heretical. And to break this resistance of community, the designers of the theory formulated their arguments in mathematical, rigorous way in form of theorems. And as long as we are planning to use it, by now, these people already got Nobel Prize for their developers. Most of the world believe that DFT is good, but just for academic purposes, we need to be aware of the theorems. And if any of your colleagues in the future tell, like, how can I believe the results that you generated? You can answer, whatever I've got is justified by mathematical proof of the theorems. And this is formulated as two theorems, and I'm going to focus one theorem per lecture. So here is the basic summary of what we are going to do in this chapter. So there will be two theorems, and then we will go to practical algorithm for DFT in the same way as we did for geometry optimization and for Hartree-Fock. There will be a flow chart that tells how self-consistent improvement of electronic structure. And then we will speak about observables that will be our main key to get through the research projects. So I am not sure if I need to go, I will quickly go over a summary of what we did last time. So the Thomas Fermi theory deals with, so it is not DFT, it is proto-DFT that describes a world where there are no molecules, there are only electrons. And these electrons do not repel each other, but it is a multi-electron system, like electron gas, same as ideal gas in thermodynamics. So one makes a trick of chopping this universe on boxes, applying equation for particle in a box for each box, and then introducing the density as number of electrons per box divided by volume of the box. And through this derivation, one can get the answer that total energy of such system can be expressed as integral of density of electrons defined in each point of space. So it is not a proof. It will not help molecular chemistry because this is oversimplified theory, toy theory, but it shows a logic that if one knows the density, one can find total energy. And now we want to expand this approach to molecular systems. And in order to do so, one needs to introduce theorems that will justify that the similar approach will work for molecules. Here is just a review of definition of functional. So functional is a function of function. And the simplest example is number of electrons, which is just integral of total charge density in power 1. So just by and it can be proved. In the same way, one needs to find the total energy as some mathematical procedure as a functional of the total density. Okay, the community of researchers, developers of density functional theory use slightly different terminology, and it's too late to teach them our terminology. It's better if we just learn their terminology and learn how to practically use it. So you do remember that if we neglect motion of nucleus, then molecular Hamiltonian or whatever electronic Hamiltonian reduces to kinetic energy of electrons, attraction of electrons to nuclei, and electron-electron repulsion. In Thomas Fermi, we had only kinetic energy. In true molecules, we will have attraction to nucleus and electron-electron repulsion. In the terminology of DFT developers, the attraction of electrons to nuclei is referred to as external potential. So it is external because the major challenge of electronic structure theories is to take into account electron-electron repulsion, which is the biggest challenge. So we are basically focusing on system of interacting electrons. And the attraction of these electrons to nuclei is external in respect to the cloud of electrons. Is external to the cloud of electrons. And on the bottom line, there is explicit equation, so it's just Coulombic attraction. But for the sake of theorems and their logic, they call it just external potential. So those who watched these lectures on YouTube in the past, or those who visited any of them in previous years, please do not answer right now. But those who are looking looking on this slide for the first time, please try to play the Wheel of Fortune. So we need to guess a word, and I will explain what we are trying to guess and find. So the theorem that we are going to prove is that the density, if known, does define external potential. And external potential, if it is known, does define total energy. So typically in our common logic, when we do Schrödinger equation and wave function based theories, our logic goes opposite. As soon as we know external potential, positions of ions, right, we can reconstruct either density or total energy, right? Here we want to invert direction of logic and tell that if density is known by some reason, one can reconstruct external potential and total energy. And the theorem, again, theorems are not derivations of equations, are not algebraic things. It's more logical exercise. So there are several strategies to prove theorems. And one of the strategies is assume that this logic is wrong and then derive logical consequences that will show that if it is wrong, then the whole universe will shake and drop. So that something will go wrong, something will be non-logical. And the Wheel of Fortune assignment for right now is to guess a word that is, I don't know, synonym of idiotic, crazy, silly, stupid, wrong, non-logical. So please try to either give a word or try a letter.
E.
Which one?
E.
Brr, no, it doesn't work. Okay, let's try another. Hadassah?
I.
Which one?
I.
I no. So there is no E. There is no I. Hanmant, do you have a guess of any letter? Just try randomly.
D.
Yes, Hanmant gets 5 points. Okay. Amara, would you like to try a letter or guess a word?
A.
Yes, Amara gets 5 points. Okay. Umar, would you like to try a letter or guess the whole word?
I guess R.
H?
H or R.
H or R?
Yes.
H, no. R, yes. Yes. You're getting 5 points. Amir, would you like to try a letter or guess the whole word?
C.
Which one?
C.
C?
Yes.
C like cat.
Yes.
No.
Mm.
Okay, let's go on the second run. Haley?
I. No, we already did.
No, I was not. Someone was already guessing it.
O.
Oh no, there is no O. Okay, we are getting closer. We will exclude the whole alphabet. Hadassah, any letter or word?
Add letter U.
U, yes. Hadassah gets points. Hanmant, a word or a letter?
M.
M?
Yes.
No, there is no M. Amara?
B.
Which letter?
B.
B.
Yes.
Like bright. Yes. Amara is getting points. Okay. So last letter of the whole word. Amir?
We try I.
Sarah? I don't know if you got chance to guess.
O.
Huh? Which letter?
O.
No. So no. O was already suggested. So anyone?
What about S?
Yes, Umar, you won. So absurd, right? Do you recognize this word? Did I describe it correctly? So like something crazy, unlogical, wrong, silly. So we are going to guess that the definition, the reconstruction of potential out of density is not possible, is ambiguous, and then we will arrive to something that will be absurd from pure logic point of view. There are different ways to name this trick. So absurd, in Latin, they call it ad absurdum, or like from contrary, whoever were taking extensive mathematical courses will recognize this method. It is used in several calculus theorems. Cock-eyed, derisory, idiotic, laughable, ludicrous, nonsensical, preposterous, ridiculous. Okay. So I'm proud of myself to use this picture from Wikipedia in this course. Anyone wants to guess what is the connection between the criminal, fingerprint, and density functional theory? Haley, would you like to try?
It's the density is unique to the system.
Yes, excellent, excellent. Thank you. Hadassah, would you like to add anything to discussion?
Or what Haley said sounds good.
Oh, okay, so if one wants to like identify a criminal by police database, one can look on the fingerprint and recognize which person was responsible for this fingerprint, right? So although the person is a source of the fingerprint, direct logic goes from person to fingerprint. But if we see a fingerprint, we can recognize who created it. And here is the logic of the first theorem of DFT, the density functional theory. First Hohenberg-Kohn theorem. So as we go through the rest of this meeting, I'm going to fill these boxes. And it was a homework. I should think, I will fill these boxes myself. Maybe we can arrange it as a homework to fill it at home or online, but let me just go over right now, or maybe if there will be movable units, I can invite someone just to shift them on the screen. But in the first red box, we will set, at the beginning, we will set up that the density doesn't give a unique potential and unique energy. And at the end, we will get some ridiculous, absurdic mathematical consequences. Something like A plus B is bigger than A plus B, which is not a big deal for those who is far from math, but for math people, it is like insult. Okay. So the boxes that contribute to the proof of this theorem. So we start from the necessity to prove that density is sufficient to one-way unambiguous reconstruction of the potential. We will try from contrary or from ad absurdum. Ad absurdum. Absurdum. So we set up wrong hypothesis that from one density, one can extract ambiguous two external potentials and two total energies. And to go through the proof, we will use another input data point, the variational theorem that we went through like 3 weeks ago. And by combining this wrong hypothesis and variational theorem, we will arrive to the mathematical consequences that total energy for branch A and branch B is smaller than total energy of branch A plus branch B, which is wrong, right? So it should be equal, and we will prove that it's smaller. And from this consequence that it goes to ridiculous absurd, we will make the conclusion that the hypothesis in the top center box was wrong. And there is only one external potential stemming from the correct total density. Make sense? Okay. So the total energy based on our experience in wave function methods is expectation value of Hamiltonian, right? So we need to know wave function, Hamiltonian, and then we can get energy. If we create a little increment to the wave function, if we manipulate, if we perturb wave function to any level away from the ground state wave function, the expectation value of Hamiltonian will increase, right? So variational theorem. So if you have different wave function different than the one for the ground state, you will get bigger energy. Okay, let's keep going. Now we are going to do several manipulations. So this modified wave function will be called psi b. And now we, anytime we do mathematical derivations, it is always allowed to add and subtract the same amount from anywhere, right? So from the last slide, top line here is the last line in the previous slide, and the only two things are different. We add and subtract the red boxes, H sub b. So this H sub b would be the Hamiltonian that would give the ground state psi b and total energy E sub b. So originally we assume there are two branches, one branch psi a, another psi b. For branch A, we have wave function psi a, Hamiltonian psi a, HA, and total energy E sub a. For branch B, we have wave function Hamiltonian and total energy with index B. Now we are trying to establish connection between them. So if we started thinking that psi a is our ground state, then we come to this equation, and if we practice this adding and subtraction, we can get two terms on the right side. The expectation value of the difference between Hamiltonians and expectation value of Hamiltonian B in terms of its ground eigenstate psi b, which will give this energy E sub b in the green circle. So please confirm that this logic is either okay or more or less okay. If anyone vote by Zoom, not applaud, but Zoom's thumb up. And if you disagree, just show that you disagree. We'll discuss it more. Okay, no one disagrees. Let's try going further. So, now let's try to start the logic in the from the other end. Now, if we have two ground states, two Hamiltonians, two wave functions, let's just swap, replace A with B and B with A. let's assume that E sub B is the lowest energy. So let me just check. Yeah, I will do it later. So now, before going further, there is one more step. We should decompose Hamiltonian on what it is constructed from. So Hamiltonian for both branches A and B includes kinetic energy, external potential, and electron-electron repulsion. The operator, so those are not eigenvalues, those are operators. So operator of kinetic energy of electrons is the same for branch A and branch B. Operator of electron-electron repulsion is the same for branch A and branch B. Therefore, the subtraction of two Hamiltonians equals to the subtraction of two external potentials. And in a couple of slides, I am going to swap A and B, but here we see that energy A is smaller than this expectation value of subtraction of external potentials. And it on the far right side, it has total energy of the branch B. Now, there is a little, I do not know how to call it, reformulation of the procedure of how to take expectation value. So when we practice quantum mechanics, we have bra operator cat to find expectation value, right? We have, or we have wave function conjugated, wave function without conjugation, and operator between them that should be integrated. If we do not have wave function, if instead we have only distribution of charge density, or if you want to make connection with Copenhagen interpretation of quantum mechanics, if you have only probability distribution. So the expectation value will be defined as probability distribution times the thing that we need to average and integrate it over space. So this expectation value of the subtraction of external potentials can be referred to in terms of integral that includes total density in branch B times the subtraction over the space. So we are going from the world of wave function to the world of density. Okay. And now we create two equations. First equation, where I would put a little star, is what we had before. So total energy of branch A is smaller than total energy of branch B plus the subtraction of the external potentials times density of branch B. Now, we do not have information which of the branches A or B is more superior, which one is senior, which one is junior. So we just assume that there are two branches. And therefore, if we do not know which one is better, we can swap indices, like replace A to B and B to A. And the second equation, where I put two stars right now, is the same style equation for the second branch. So total energy of branch B is smaller than total energy of branch A, plus the subtraction of external potentials times the density of branch A. Please confirm if the logic goes okay up to now, or show if you do not like it, just show that you're not happy. Okay, yeah. Thank you, Hadassah. So these two equations both originate from variational theorem. If you go from one wave function to another, energy must increase. So a variational theorem is responsible for this inequality sign. And the subtraction and different energies here originate from a trick of adding and subtracting the same object from the correct expression. Now we do have two inequalities. They use different densities, density for branch A and density for branch B. But our original logic was that we have only single density from which we get these two different branches. So if you have only single total density, then density for branch A and density for branch B must be equal, right? And if it is equal, we can just remove the index A and B here and perform subtraction of these two lines from each other. So when we perform subtraction, here there should be no index. When we perform subtraction, you see that this term and this term are equal with precision up to sign. So if we subtract, not subtraction, we add together. When we add together first and second equation, then the energy A and energy B are added here and there, and this complicated term is completely removed, subtracted. And as a consequence, we have the equation total energy for branch A, total energy branch B is smaller than total energy branch A plus branch B, which is considered non-logical, ridiculous, absurd. So if we believe this logic, if we do not see logical flaws in this theorem, in this proof, then we should admit. So if this was if this consequence was false, then it means that original statement was false, that we are not allowed to say that same charge density leads to alternative branches of observables. So if same density does not generate branching alternative observables, it means that it leads only to one branch of observables, including the external potential and total energy. So knowledge. Anyone is speaking?
Yes.
Yes, please.
So I'm just trying to understand that talking about A and B, I thought B is is as a result of when you perturb A, which is assumed to be like the ground state, right? Is that what it is?
Yes.
So why are we assuming that their densities are equal if they are supposed to be different, since we're going from one state to another?
Yeah, thank you, Lola. We did assume, let me go to the start of this derivation where you have the flow chart. So we did assume that there is only one density. And from one density, we can get different external potentials and different total energies. And here we do not specify which one is better than the other. So you are asking why? Please repeat the question. I just want to repeat your formulation.
Yeah, so I'm saying that, like, if we're assuming that B is supposed to be like a correction of A, why are we assuming?
Yes, B is assumed to be correction of A.
Yes, so why are we assuming
Yes.
that their densities are equal?
Yeah. So you're so always asking B is correction of A. But since there are two branches, at the same time, we can say that A is correction of B. So we start from the beginning. We are telling that we assume that there are two energies, two branches of all observables that stemming from the same density. And the paradox is coming immediately. We just want to bring it up more explicit. So we start discussion telling that B is correction of A, but at the same time, on the second piece of paper, we restart the same derivation where we tell that B is our minimum and A is a correction of B. Like I would redraw it in the parallel, like E B smaller than psi B plus delta psi H B psi B plus delta psi. And then you can put prime to be non-specific. And this will be psi A. Does it address your question or make situation more complicated?
No, I understand now. For the fact that, like, it's either A is a correction of B or B is a correction of A. So yeah, it makes sense to do that.
Okay. Okay. Yeah. Many thanks for asking this question. So the theorem that we have proved is not a style of constructive thinking. It's not a style of thinking to solve any problem. This is made by humans for humans to assist the arguing. So this logical paradox is made to disarm those who will tell that density is not sufficient to find total energy. So the theorems themselves are not included into any codes, into any equations that are used to find electronic structure of molecules. It is only a logic to convince people that those protocols that we will discuss later are correct. Make sense? And if it will be just a protocol for computation, then this DFT will be not as popular today, and people would be not convinced that it is useful, and the designers of DFT will not get Nobel Prize without proving these theorems. So basically, we are looking on the path how to get Nobel Prize. Prove a couple of theorems. Okay. So let me check. I feel that it is about the last slide. Or, okay. So by filling the proof in the middle and showing that the hypothesis was wrong, we proved that there is only one. So the density determines external potential and total energy. The theorem, this theorem that we have proved, is not a solid thing on its own. It is a step to go to the second theorem that we will cover in coming Monday. Okay. So total electron density determines all observables, determines external potential, and total energy of the system. We are about done. Let me go to the middle of this lecture and focus our attention on any of these equations. Maybe here. So right now, we are not making any practical connections to real life, but the expression in the box opens a little door, shows how the practical ways in density functional theory work. So by integrating density times potential over space, one is getting contribution to the energy, right? And if one makes integration of density with other potential, one can get the total energy. So total density is known, and one just needs analytical expression for these potentials, which is somewhat quicker than Hartree-Fock procedure. But we will get through this conversion of density into energy with more details when we meet again. So this year it is number 19 because we have so many attendees and we need to present more frequently. The meeting is done. Everyone is welcome to come to the lab tomorrow evening, and we need to cover. We will shuffle the materials, but to hit the time. But there are several skills that we need to cover. So we do need to learn how to plot orbitals. We do need to learn how to find absorption spectra, and we do need to learn how to run ab initio molecular dynamics. So those are minimal amount of skills: orbital, spectra, molecular dynamics. In addition, so there are three more things that I will try to instruct as time allows. So key points, dependence on momentum, which is important to those who will describe periodic solids. So momentum dispersion, spin, same as we did with Gaussian, spin up, spin down the systems with unpaired electrons, magnetic materials, and metal organic complexes. And the last but not least, everything we do we should be able to run it either on photon or on a remote powerful cluster. And for the sake of academic learning, I can put the cluster as a very last thing, but for the sake of later success in the projects, maybe we should start with learning how to run VASP on a cluster right away when we meet tomorrow, because it will be, there is nothing new in principle, but the skills of transferring files and using slightly different commands will take time, and it is better if we invest this time right away and have the skill ready when it will be time for doing projects, because some of you already contacted me, and I see that you guys are looking to relatively large systems that photon will not be able to treat. You will need more powerful computation. Okay, meeting is done. Everyone is welcome to disconnect and depart, and I'll stay here to answer any questions.
I have a question.
Yeah, thank you.
So help me understand. The first theory, does it assume that you can get external potential from density? So does the theory also okay, at what point were they beginning to assume that density can be split into two different external potential, which will give you two different energies? Is it also this first theorem that made this assumption, or it was people that were trying to just make sense of this, or what exactly happened?
So the first theorem uses intentionally sets up the wrong hypothesis.
Why?
So
If they know it's wrong.
So the goal of a theorem is to show that there is only one branch. From the density, we can get one and only one external potential. And if this theorem is not correct, then it means we can get not only one, but one and one another. So let's assume you can get one and one another external potential and see if it will be reasonable.
Okay, so the theorem is from one density, we can get one external potential. That's what the theorem is about.
Yes, theorem is about that one can get only one external
Only
potential.
one. Okay. All right. Thank you.
Oh, thank you. Many thanks for your questions. I really like them.
Bye.
Bye.